Okay, thank you. My name is Patrick Irvin. I'm from the University of Pittsburgh and the Pittsburgh Quantum Institute. I work in the research group of Jeremy Levy, and I'm going to be telling you about some quantum interference effects we see in sketched LaOSTO Hall bars. So quantum interference can manifest itself in several ways in two dimensions. We can have localization effects um, in which scattered current paths will either constructively interfere in the case of weak localization or destructively interfere in the case of weak anti-localization. As we move away from the diffusive regime, we can have Shubnikov-de-Haas oscillations at high magnetic fields. This is when resistance oscillates with a period that's periodic and 1 over the magnetic field. These are two examples from the Triscone group and the Dagan group, seeing Shubnikov-de-Haas and LaOSTO. And also we can, this is another example from LaOSTO in which the Caviglia group sees, they've made squid devices in which, so there you have a superconducting loop with two weak links. And here you see a macroscopic manifestation of quantum interference. And we just saw two great talks from their group. So now what if we move to one dimension? Here you have something called the Aharanov-Bohm effect, which was first seen in the solid state by Webb in 1985 in a polyimide ring. So here they see oscillations of the resistance that's periodic in magnetic field. So the Aharanov-Bohm effect happens when you have a current conducting channel that you then make flow through a ring. So you have I, it splits, goes through left and right channels. If you apply a magnetic field perpendicular to that ring, there will be a magnetic vector potential that surrounds that out-of-plane magnetic field. And the current going through the left and right halves of that ring will acquire a different phase. And that phase difference will give you an oscillation period given by given by h over e, and here phi is the flux. And then you can calculate a period, and this is the period that they saw in that paper, in the Webb paper. So real briefly, for this audience about LaOSTO, has many diverse properties from superconductivity and gate tunable superconductivity. There's been many reports of magnetism at the interface. And then, so these are examples of LaOSTO is a two-dimensional electron liquid, but there has been recent examples that have shown that one-dimensional effects can become important even in a two-dimensional device. So this was shown by the Moeller and Elani groups where they observed this channel flow and that resulting from the ferroelastic domain walls coming from the tetragonal, coming from the strontium titanate substrate. So what we do in our group is create nanostructures using atomic force microscopy. So we begin with 3-unit cells of lanthanum aluminate grown on strontium titanate. We etch electrodes that contact the interface. We next introduce a conducting AFM tip. If we apply a positive bias to the tip, we can deposit protons on the surface. Those protons will attract electrons to the interface, giving us a conducting channel at the interface. If we apply a negative bias to the tip, we can create barriers in those wires. We can create constrictions. We can erase the protons and start over and make a new device. Typical dimensions are, we can make wires as small as 2 nanometers. Typical widths of these wires are about 10 nanometers. So we've seen several things in recent years using these sketched one-dimensional structures from single electron transistors. We've observed just this past year electron pairing without superconductivity, in which electrons begin in a paired superconducting phase, but then move into a paired phase up to a critical field that's pretty high compared to the superconducting critical field. We can make quantum point contacts in which we control the number of quantum channels in a wire. So here we are seeing conductance jumps of 1e squared over h at high fields. And finally, we can make Fabry-Perot cavities, which show that we have coherence lengths on micron length scales. So, so what we would like to do is observe quantum effects, quantum interference effects in these AB ring devices. So here I've drawn a device like we created with the AFM. This looks a lot like typical AB ring. So dimensions are a few microns for the diameter of the loop and wires of 10 nanometers in width. So we run current through that main channel and measure the voltage drop across the ring, giving us the longitudinal resistance V over I. So this is typical magnetoresistance data. And the thing I want to point out is that there's no quantum interference. No quantum interference. We've looked at dozens of devices with various kinds of geometries. From the typical AB ring I just showed, we've made rings that are filled in. We made rings that are filled in with different densities and cuts inside. We've made cuts inside the ring to try to ensure that we force the current into a left and right path. We've even made square rings. And in none of these cases have we ever observed quantum interference effects. So we're interested in making many kinds of devices, and another device we typically make is a Hall bar. So here I'm going to show you this is a pretty wide Hall bar. So this is made by raster scanning the AFM tip to sort of fill in a wide region. So this device has conducting channel width of 250 nanometers and a length of 1.5 microns. Again, we run current through the main channel, measure the voltage drop to give us a longitudinal resistance. So now if we look at the longitudinal resistance as a function of out-of-plane magnetic field, we first see a weak localization peak at 0 field, no oscillations up to 2 Tesla, no oscillations up to 4 Tesla. Now as we approach 6 Tesla, we begin to see some oscillations. And I'm going to increase the field even further. And lo and behold, we observe quantum interference in these Hall bar devices. So we see the interference above some critical field of about 5 Tesla. If I zoom in, we can see that there are two periods visible here, about 0.25 Tesla and 0.03 Tesla. We can reverse the direction of the magnetic field. You see a shift in the profile of the field. And if we zoom in, it's not quite visible very well here, but there's also a shift in oscillation period. So we can see this by looking at a power spectrum. So this is a Fourier transform of the magnetoresistance. And there's many peaks here. I'm going to focus on 4. So the forward sweeps are in red. So we have 0.029 Tesla, 0.014 in the reverse direction. So this is just a reminder of how we can calculate an area that would be associated with a signal that's periodic in magnetic field. So we have these 4 signals. I'm going to calculate an area. So these range from 0.129 microns squared for 0.03 Tesla to 0.295 microns squared for 0.014 Tesla. Now I'm going to draw the device, and I'm going to do an ansatz of dividing by the channel width. So if I take the last curve of 1.18 microns and I draw a loop of 250 nanometers by 1.18 microns, basically I can superimpose that on the channel we have available. These are the dimensions again. It could be that a loop is not exactly those dimensions. Maybe it doesn't go out to the width of the channel, in which case I've drawn a loop with a different aspect ratio, but we can still see that a feasible loop would fit in that channel. So how do we explain these features that I pointed out? First of all is the critical field of about 5 Tesla. This is consistent with our observation of electron pairing without superconductivity. It may be that we only observe this quantum interference effect above the critical field after those electrons have depaired. We see hysteresis. This just may be an indication that or confirmation of magnetism in the system. And finally, how do we make this kind of crazy current path in this wide conducting channel? One possibility is that we have carrier depletion, in which carriers are depleted away from the edges. So this is discussed more by my colleague in this talk here. It may be that there are magnetic scatterers in the current within that channel that will scatter the current to left and right paths. And finally, as I sort of alluded to earlier on, is we may have current flowing along these ferroelastic domain boundaries. So this loop I've drawn in PowerPoint may actually be defined by the ferroelastic domain boundaries. So real quick, in conclusion, we have observed quantum interference in 2D devices, and we do not observe quantum interference in 1D devices. Thank you very much.